Alright, let's do a practice circuit. Let's do a very complicated one. Banana. Then why'd you speak it first? Not this circuit. Very simple circuit. Compared to most circuits. They have large concentrations of mercury. Oh, and this will be the positive side, this will be the negative, and let's make this 200. Note that the units for this is VDC. Does anyone know what that stands for? VDC. It stands for voltage direct current. Alright. So the question is, how much current is flowing out of the battery? So, what is in series and what is in parallel? What is in series and what's in parallel? So what does it mean to be in parallel? Remember, parallel shares same wires. And to be series, no branches in between. This is the circuit I'm going off of. So the trick of this is to find something in series and find something in parallel and replace it with a single resistor or a resistor with the equivalent resistance. So, do you see anything in series? Do you see any two resistors that have no branches between them? So, here's two branches between these two. And there's a branch right there. So if we look right here, we see no branches right here, but we see two resistors connected. So this would be what? It would be in series because there's no branches in between. Where it splits off, yes. 77 and 100? Yes. So it branches off here, and it branches off here. So this one has two branches on the other side, so it's not in series with anything. So is there anything in parallel? Where's 185? Oh, 185 here. This would be in parallel. So if we look and draw the wires, so I'm going to darken this wire. Note that this whole thing is considered a wire until we connect it into a resistor. So if I color code this, we see that both of these share the same wires. Yes. So they share the same wire, these two. The 100 and which one? This one? This one? No, because there's something in between. Yes. So these do not share the same wires. Because look at this 85. This one has this wire right here. But that's not the same wires connected to this one. This one, if we look, is in parallel. So we color all of this wire. So this is one wire. This is in parallel. So these two are considered to be in parallel. This is probably too much to do at once. I highly recommend you do one step at a time and do it, combine two resistors at once. But to really illustrate that these two are in parallel, let's color them. So you need to be able to do what I just did and look at it without using colors. Alright, so we can see which ones are in parallel because they share the same wires. So as we already saw, these two share orange and blue, so it's parallel. These use lime green and purple, so they're parallel. But you said earlier this 185. This 85 has orange and blue. Well, this one has green and purple. So, the next step is to replace the ones in parallel with a single resistor, the ones in series with a single resistor, and then calculate the equivalent resistance. So we're going to have to redraw the entire circuit, but replacing those we've labeled as parallel with a single one. So this right here is going to be replaced with a single resistor. So this was our 63 ohm. This is our 77 ohm right here. So when we're replacing all of this, we can see the connection points are right here, and right here. So we can see that this was all one wire. So we can connect this all the way down right here. So this point right here and this point right here is connected with the same wire. And we can see that these two are going to be connected. So we can replace this with a single resistor right here. And these two can be replaced with a single resistor too. Like this. So this was our original red wire. This was our 50 ohm right here. Yeah, so you'll just add those together. Yeah. We can see that this green wire right here was connecting the 77 and the 50 together, so it remains here. Just tenderly right. We see connecting the 63 with these two was connected with this blue right here. Connecting the right sides of this one was purple. So the right side of these two was purple. The right side of these two were purple, so we keep that the same. And then the last color we have Alright, so we combine these in parallel. So the parallel rule is that the equivalent resistor is equal to 1 over 1 divided by 25 plus 1 divided by 50. That's our equation for combining two resistors in parallel. And make sure you put the denominator in parentheses before putting in the calculator. So that is equal to 16.667 ohms. So we can go ahead and plug that in right here. 16.667 ohms. So that was the equivalent of this one. In series, we just add them together. So the equivalent of adding together is just 85 plus 200, which gives us 285. So that's 285. And these two were in parallel, so we use our parallel rule. 1 over 85 plus 1 over 100. And put those in parentheses. And the equivalent resistance is 45.956 ohms. So this one is 45.946 ohms. No, so in parallel we use this equation. In series we just add. So if we're in parallel, we're going to use the reciprocal of sum of reciprocals. Alright, do any two resistors use the same set of wires? 50 and which one? So 50 uses red and green, while 63 uses blue and red. None of them, so none are in parallel. Are any in series? Which two are in series? 77 and 285. There's a branch. Alright. So there is no branch in between. So these two are in series. Are there any other ones in series? Yes, so these two are in series. There is no branch on that purple wire. So these are in series. So we redraw the circuit, replacing those in series with a single resistor. And this would have been 200 volts. Make sure the shorter side stays on the shorter side and the longer side stays on the longer. You don't want to put your batteries in reverse. Alright, so we're going to replace these two with a single resistor. So we'll replace it with a single resistor. The equivalent resistance is just the sum. So that'd be 16.667 ohms plus 63 ohms. And the equivalent resistance is 79.667 ohms. Yes. This resistor didn't change, it's still 50 ohms. This one doesn't change, it's 50 ohms. And these two are going to be replaced with a single resistor. And the equation for that resistor is just 285 plus, yes. So we had orange coming out of here. And we had red coming out of the battery here. So we continue drawing red on all wires as we bump into a resistor. And we had a green on the other side of the 50. So, is anything in series? No, nothing would be in series. Is anything in parallel? Anything share the same wires? Yes, so they share orange and green. So these are parallel. So these are in parallel. So we'll come over here and replace the circuit again. Yes, this is the battery. The battery is 200 volts. Yes. There's our 50. And we're going to replace all of this with a single resistor. And its value, its equivalent resistance, will be 1 over 1 divided by 77 plus 1 divided by 330.946. Yes. Not really. Yeah, but all we're doing is replacing with equivalent resistance. So we use this equation, and you're right, there's no branches now between this, so this will be in series. So to replace that, it would just be, so with series, we just add them together. So we redraw the entire circuit again. About 20% of the tests will be questions like this. Yeah, but that'll be a lot simpler. No. So I'm replacing those two that were in series, meaning up. So replace that with the equivalent resistance of 112.406 with a 200 volt battery. So these share the same wires. So if I darken this wire, we can see that they both share this wire up here. I darken this one, so they're parallel. So, so we apply our new equation, 1 over 1 divided by 76.667 plus 1 over 112.466. And make sure you put this in parentheses. Yes, put it in parentheses when putting in the calculator. So this whole circuit has a total resistance of 46.6335 ohms. Not really. So the total resistance is 46.6335 ohms. And the question asks how much current is leaving the battery. So this longer side is going to be your positive, and the shorter side is going to be the negative. And we draw conventional current flowing out of the positive terminal. So the total current is equal to the total voltage over the total resistance. So 200 volts over 46.6335 ohms. which equals 4.28876 amps. That's what current is measured in. Yes, you can write out amps are a capital A. You put your mask on properly. Everyone good? That was a complicated example. Yes. So that was actually a very small circuit compared to real circuits. Real circuits like in your computer, your phone, your TV, or any appliance will be huge. So let's do a few more examples. So let's do one like this. And let's do it without using any colors. No. Alright, so R1 is equal to 10 ohms. R2 is equal to 20 ohms. R3 is equal to 30 ohms. R4 is equal to, let's continue this pattern, 40 ohms. And R5 is equal to 50 ohms. Yes. What is the difference in R1? Very complicated. It's outside the scope of this level of class. In physics class, that would be solvable. Or not going that in depth into it. So what is in series and what's in parallel? So R3 and R5 is in series. Let's stop there and just immediately go ahead and combine it. That's a very simple calculation. So R1 was 10 ohms. R2 is 20 ohms. R4 is 40 ohms. And we're replacing both of these with a single resistor that would be equal to 30 plus 50 is 80 ohms. So I replaced it with that 80 ohm resistor. Is anything else in series now? 20 and 10 has a branch between them. Nothing is in series. Is anything in parallel? So let's draw the wires and connect them all up. So they both share this top wire. And if we draw the bottom, they both share the bottom. So they're in parallel. You could also realize that 80 is also in parallel, but you don't have to do it right now. We can just work with these two right now. You could have combined all three of these at the exact same time. So these two are in parallel. So I can replace them with a single resistor that they're connecting between these two resistors. So here's the 80. So they're connecting here. So I can draw, they're connecting at that point, I can draw a single resistor here. And I can just connect it up like this. So our equation for this these two combined is 1/1/20 plus 1/40. Make sure to put that in parentheses. Yes, these two were in parallel. Yes, so they can't be in series because there's a branch here and there's a branch there. Only two of them are in parallel. So we replace these two with a single resistor. So I collapse this down, moving this wire over to this point, and made it a single resistor. Now again, we can look and see that these two share the same wires. So if I connect I can connect the bottom of this resistor to the right of this resistor, and I can connect the top to the left of this one. So these two share the same wires. So these two are in parallel. Note, I could have recognized that all three of these were also in parallel and did 1/1 / 20 plus 1 / 40 plus 1 / 80. And got 11.42857 ohms. However, we decided not to do all three at once, but only do two at once. So if I now apply my equivalent resistance, so let me first redraw the circuit. So I'm replacing these with one resistor, and I'm going to use the equation 1 divided by 1 divided by 80 plus 1 divided by 13.33, so on. And I get 11.42857 ohms. So this value for this resistor is 11.42857 ohms. So you can notice that if I did all three at once, I get the same result. Or if I decided to do two at once and then do them again in parallel, we get the same result. So no matter what order you do it, it's all going to converge to the same thing. Now if we look in between them, there is no branches. No branches mean they are in series. And series, we just add them together. So series is 10 plus 11.42857. And so that's 21.4287 ohms. So our answer is 21.4287 ohms is the total resistance. Yes. I'm really spacing this out more. Battery should be closer together. That's a better looking battery. How much time we got? So I've written people who missed the test but need to make it up. Also written people who don't have to turn in homework. But tomorrow I'll give out homework.